Hello, in this video, we will be discussing our work CLEO, Continual Learning of Evolving Ontologies, presented at ECCV 2024. This work is a collaboration between the German Research Center for Artificial Intelligence, the ZF Group, and the University of Kaiserslautern-Landau. Continual learning is a paradigm where a trained model is continually updated with new tasks. Depending on the objective of the new task, there are two incremental learning scenarios. In class-incremental learning, previously unseen and non-overlapping subsets of classes are learnt in each task. Whereas in domain-incremental learning, the classes remain the same, but new input distributions are learnt incrementally. Continual learning mimics lifelong learning in humans, where we continuously acquire new knowledge over time without completely forgetting what we've already learnt. However, the learning process is not limited to learning new information but also refining existing knowledge. For example, we first recognize animals broadly, and then learn to identify specific species. We propose CLEO, Continual Learning of Evolving Ontologies, a novel incremental setting that emphasizes refinement. Unlike traditional CIL, where all new classes are entirely novel, CLEO allows for the refinement of previously learned classes. For example, in CLEO, a model might initially learn the class, vehicles, and later refine it into more specific classes like car or bus. CLEO also supports traditional CIL where entirely new classes are learnt. A real-world example of CLEO is found in Mapillary Vistas, with label expansion. For the same set of images, the number of classes expanded from 66 in the initial version to 124 in the current version. Among these classes, some are entirely new and were previously unlabeled, whereas some classes were previously part of larger classes. In incremental semantic segmentation, knowledge distillation can cause background shift, where new classes were previously labeled as background, leading to mismatches between the predictions of the current model and the previous task model. Modeling the background, MIB, addresses this issue by combining the predictions of the new classes and the background class. In CLEO, this issue extends to an ontology shift, as the current classes being learnt weren't necessarily part of the background previously but rather may have been part of existing classes. We address this issue with Modelling Ontologies, MOON, as a baseline solution for CLEO, by combining the predictions of refined classes with their parent classes. We present 7 CLEO task settings, using 3 datasets, namely, Cityscapes, PASCAL VOC, and Mapillary Vistas. These settings differ in the splitting order, either all from a single parent class or one from each parent class in each task, resulting in different number of tasks. Using PASCAL VOC, we explore different class granularities, experimenting with intermediate splits into subgroups and retaining subgroups of classes. We evaluated our approach by comparing it with existing class-incremental learning baselines, including MIB, PLOP, and RCIL. The results across various task settings demonstrate that MOON consistently outperforms these methods. This highlights the limitations of traditional CIL approaches in effectively adapting to the refinement of existing knowledge, a key aspect addressed by CLEO. Thank you for watching.